day. Right. Okay. So look. I've been doing a bit of research. So we are actually going to have a little bit of a social experiment in all of this. So if I hit that, there we go. Right. So I've been doing a little bit of research into teaching, basically, because I'm now an associate lecturer at Anglia Ruskin, and it turns out that after 10 minutes of concentration, things rapidly go downhill. And usually, after about half an hour, your brain's just a little bit frazzled. So we've got quite a bit I want to share with you in two halves. So my plan is, in about sort of half an hour, we'll have a 2-minute break. We can grab a glass of milk and a biscuit. Yep, and then we'll carry on. And in theory, I'm told that then this will then sort of re-peak one's concentration. And so maybe you can tell me at the end whether that's a flyer or not, whether you like it, whether you don't like it, whether we keep it, whether we chuck it for the next time. So there will be a little break, not really long enough to put the kettle on, unless you've got a fast boiler, but we'll see what happens. So just the usual bit of housekeeping here. So this is like the most usual problem I have here is sometimes the internet link drops and I don't know about it for some time. In fact, since the screens I've got here, I cannot even see the internet connection. So I may be a while before I realize I'm talking to myself. Everything we've got here is available to download. So you don't need to do screenshots or anything like that. If you hop along to the my website and scroll down to see downloads, and that's your documents, there's a folder in there, season 3, which is what we're on, and these slides and the firmware, which we're going to have a look at. It's all there, all ready to rock and roll. You can grab it at any time and use it. No problems at all. Right, okay, so this evening's entertainment is all about vibration on using the Raspberry Pi Pico. And we'll have a little look to start with at setting up the SPI on the Pico. There's a few elephant traps which I've discovered recently. And then after our little break, we'll then have a look at some how you can use accelerometers for vibration. Right, so this is try to get all that stuff in the first 10 minutes nonsense. Right, vibration. So here's a few shots of what you might get from a vibration. So just to explain what's going on here, just as a whirlwind tour, the top left one, NO, that's if you had a really good working bearings, fresh out the box. That might be an example of what you see for a bearing race. To its immediate right, that's the same thing with a little bit of wear. And then the right and the ones at the bottom are just examples of when things might suddenly go wrong. And you can clearly see that there are some definite sort of patterns, although IR is the inner race problem, OR is the outer race, and of course, trying to detect the outer race or just a bit of wear seems to be quite difficult to distinguish between the two. And RE is if there was a rolling element problem, and CA is if there's a cage problem. So can we use an accelerometer to try and detect any of these problems is the name of the game. And we're going to be using MEMS accelerators, micro engineering devices, for which one is here. So there are many flavors of these accelerometers. Is one any necessarily better than the other? No, not really. I found if we're doing vibration, all the stuff I've done is I generally find that one axis seems to be quite plenty for something that's vibrating. So the X, the Y, and the Z, if you processed all 3 axes, then you've got 3 times the amount of processing. And if you're using a small microcontroller, if you're on something like the Arduino Uno, the 328P, you might start to have a memory issue. But I thought it's worth looking at a issue with these MEMS. So this here, which hopefully you can all see, this is an electron scan of just a accelerometer, which I found online. Seems that if you ever dig around on Google, there seems to be zillions of different topologies for these designs, but they all basically have the same sort of thing. You've got, you see where it says capacitor, which looks like two combs. So when the thing vibrates, you've got a floating mass in the middle on some springs, and this is all etched, you know, probably about 60 microns by 60 microns. So as the whole thing vibrates in those tiny black packages, which we see on devices, we've got one here we'll play with, you can see those what look like two combs will move in and out, and basically they're capacitors. And that's exactly then how the whole vibration gets detected. Now, your first nugget for this evening is there's a little phenomena with all accelerometers called stiction. And you generally don't find it written in the data sheets unless the supplier has done something about it and they're making a song and dance that we've got stiction control. So stiction, if you ever have a little dig on the internet, it's electrostatic forces that build up in the, I guess let's call it a comb. And essentially it causes the whole device to lock up and basically stick together through static. And the way you'll see it in any code, it'll look like the device is suddenly frozen. Or you'd think my code has stopped for some reason. In fact, what's actually happened is electrostatic forces have built up in the device, and then it's just sort of stuck together. There is a way to fix it, which is our next pearl of wisdom. There we go. So this is a circuit I've used many times. It's the one we've playing with this evening. So it doesn't matter what accelerometer that you use, they pretty much all have this issue, and you've kind of got to come up with a way to fix it. So what we're going to play with and we'll look at in a bit of code is using it on the SPI bus, SPI being serial peripheral interface. You do find accelerometers also with I2C, which we've really got time to go into this evening. So we'll look at that with another sensor in a couple of months' time, January possibly. So SPI and I2C, they are on probably 99.9% of sensor chips. And the other 0.1% you probably wouldn't want to buy. So it's a data bus, for those who are new to it. You have what's called a chip select, which is selecting the chips, a dedicated line. You can see that at the top. You've got a S clock, which is the clock. We'll have a look at that in a second. Got a chat here. Blah, blah, blah. It's interchangeable. Oh, right. Okay, I'll answer that in a moment. Correct, Greg? You've got a master out, serial in, so the processor or the Pico, the Raspberry Pi or the Arduino, of course, that's your master, and your accelerometer or your sensor is always the slave. So it's master out, slave in, so it's fairly simple to follow what's going on. And then, of course, MISO data going the other way. What I'm adding for you is what's called stiction control. That is, when these electrostatic forces cause these chips to lock up, the only way you can release it is to cut the power to the chip and also make sure that there is no power over the data bus. Because if there is a power over the data bus, although you've cut the power to the chip will back power and the stiction will remain. And it took me a while to discover that one. So the way this circuit works is GPO 0 here is if that's logic 0, low, then the chip is powered up through Q2, and Q3 is off, and Q1 is off. For stiction control, you need to make sure all the data lines are driven to 0 and you've got no power. So if we were to send power to Q2, it would actually cut the power to 3B3 ACC, and it would switch on Q3. And Q3 just discharges those capacitors at the top right and make sure that the power on the chip has discharged properly. What I can tell you, as I've discovered, is maybe not all chips, but certainly this one, when you either disable the chip select, you'll find that the MISO line is floating. When you enable the chip select, the MISO line is still floating, and it'll float, as we'll see in a second, until there is a clock signal, and then the MISO line will start being data out from the accelerometer to the microprocessor. But even if there's, say, a 10K resistor, you'll still be able to be enough current flowing into the data, through the data ports, to hold the stiction. So it's a little gotcha, and that is exactly how you then get out of it. To answer Greg's question here, and so you're very welcome to leave your microphone on and interrupt me at any point. Do the devices interchangeable? Well, not really. I mean, obviously SPI is pretty standard, but the code and the addresses is going to be unique per device. So you're going to have to refer to the datasheet for that. But in terms of wiring it, could I just take a different accelerometer to the one we've got here and wire it in? The answer is yes, you certainly can. But of course, the code would change for the addresses when you read the data, which we're going to have a look at in just a second. So hopefully you're all still with me. It's all very quiet. Right, now I've hooked this bad boy up here. And what I've done here is need new battery in that. Okay, one moment. Huh. Right, so PowerPoint is just frozen. Next, try that. That worked, didn't it? So, so I've actually hooked up an analyzer to this, so you can actually see what's happening in real time. So as you can see on the left there, the chip select line. So at the end of every command, and you've got to read the data sheet to get this information. What I'm finding, most devices, at the end of every command you send to the device, you then usually have to cycle the chip select. As you can see, in this setup here, my chip select goes low, which is on 0 at the top there. Then I set my stiction, and that stiction will actually then depower the chip. And then, of course, you can see the MISO line's been driven low. That's been driven low through Q1, because until there is a clock, that MISO is floating, and you don't want to back power into the chip. And then you usually just send it a command which comes out of the data sheet. And another pearl of wisdom I've discovered, because I used to have this chip running on an I2C, the addresses you use on I2C are not necessarily the same as the addresses that you use on SPI. Often there'll be bit 8, you'll have to set a bit 8 or an extra bit or B in the data sheet, which extra bit you've got to set when you're using SPI than if you're using I2C. Because I originally just ported my code across from I2C to SPI rather, and it just didn't work, and it took me a little while to do that. See, and then just by way of example, you then send in a command like E8 here, and then some clocks, and then some data coming back. So if you want something to come back over the MISO line, you've usually got to tell the chip you want it. You can't just assume it. You've got to tell it, I want data, and then the number of clocks. So in this case here, you can say we're reading 2 bytes. Yep, so far so good. Other little thing I've discovered when we're using MicroPython with these devices is when I was originally trying to read these chips and send a command with MicroPython, certainly on the Raspberry Pi Pico, if you were to send a command that say 7 bits off the 8, that say 00 to 127 or 3F, absolutely fine. You'll see the correct data come out over the MOSI line. I was finding as soon as I flipped over and was sending the 8th bit, say 128 and above, 440 and above, I was then getting a random byte come out over the MOSI line, and it wasn't in the code. And it turned out to be, don't ask me why they've done this in MicroPython, but if you set it to send 8 bits, and that an 8-bit word, and that 8 bits got bit 8 being high, it sends like a preamble. So I had to work out a way to force MicroPython to only use 8 bits. Now, if you get yourself a logic analyzer and you hook it up, you can discover all these problems and whether it's working really quickly. Whereas if you just had this coming out on the screen in a shell, I think the chance of trying to debug SPI and I2C, it's going to be extremely difficult. And you can buy these analyzers off eBay for like £13, which is nothing. So back to the story. So with data coming out of the accelerometers, or probably any sensor, they come out in 8-bit chunks. Like you see on the right here, I've got O, X, C, O, and then FC. So that's 2 halves of a word. And so what you've got to do, you've got to read that in, and we'll have a look at that, and then you've got to try and knit them together. And this is how you knit them together. So we've got reading 2 bytes, and the data is usually the most significant byte and the least significant byte. We then do a little bit of bit shift manipulation. So dead easy. And we'll look at the code in just a second. You slide the most significant bit, you just bump that left by 8 bits, which you can see there. Those 2 arrows mean bit shift left, 8 and 8 bits. Then just add the least significant bit, and then you've got your 16-bit number. So there's only a few lines of code, and we'll look at that in MicroPython in just a second. But that's not the end of the story. So although you've got a 16-bit word, it'll actually be what's called 2's complement, which is it could be a positive number or a negative. So let me show you how 2's complements works. This is first year off a degree, this bit, but we'll get through it. So if bit 15 is a test in the code, if bit 15 is 1, then you've got a negative number on your hands. And the way you actually create a negative number is with bits. There's a very simple function here, which I've got an example here just to show you. You have to do a little bit of Boolean algebra, simple bit of code, and at the end of it we add 1. So in this example here, let's say we read 65532. So bit 15 is a 1, or the end bit, say bit 16, so of 0 to 15. I've got a 1, so I know I'm dealing with a negative number. So I'm going to flip all the bits by doing an exclusive OR with 1, and you can see the truth table there. I grayed out the bits we don't use. And then that'll give us, in this case here, 3. And then you add 1, and then, because the reason you add 1, because if you had 0 or FFFFF, which is all 1s, and you flipped it to 0, you could have +0 -0, which isn't a thing. So it's a bit of a cheat. You flip all the bits and then you add one, so you can't ever have a -0 number. And if you just bear with that picture in the bottom right and I flip it, you'll see that -4 at the top becomes 65532 at the bottom. So the 3 lines in the middle never change. So depending on what you're plumbing in, -4 will always become 65532. And if you go back, you see 65532 will always become -4. So it's a nice little algorithm and it works pretty well. And all negative numbers are dealt with this. Of course, the Raspberry Pi Pico and they're all 32 bits. So the reason we're having to do this is because we're dealing with a 16-bit number to create a negative, not a 32-bit, where we probably wouldn't have to do it because it would be done for us. So there's a little bit of gymnastics. Right, okay, let's have a look at the Pico, shall we? So here it is. Right, so last time I suggested that whilst you can have any pins doing whatever you want, just about within reason, the structure I've come up with allows us to have UART, I2C, SPI, and a GPIO bus and all the analog pins. You're not tied to this configuration that I've come up with, although obviously the SPI can only be on certain pins. But another little nugget here is that the code at the top, that one after the SPI open brackets, that one refers to which of the 2 SPI ports you're going to define. So you wouldn't be able to have SPI 0 on pins 10, 11, and 8, because 0 is on, or GP, the pins 2, 3, and 2, 3, and 4, which you can see lightly grayed out just above next to I2C, or some of the other ports like GPIO 19, 18, and 17. So whichever one you were going to use, you just got to make sure you choose the right number there to start with. Right, okay, so we've got a few minutes here. So let's do some more camera gymnastics and actually look at the code, shall we? Right, so hopefully, if I unshare this, and then I am going to hopefully, if I get rid of that so it doesn't go wrong. Right, if I share it with you now, here we go. So, right, hopefully that is sharing with you nicely. So I hope you can see some code. So, where are we? Right, so important bit in my code. This code's all available to download. So just grab it if you want. So again, I've got my SPI port pin definitions here. See that one there is quite important for these pins here. And then this is one of the gotchas, which took me a day to work this bit of code out, this one line here. When you're reading SPIs into arrays, you got to use the command byte array, not just the defining an array, as a floating point or an integer. Because if you just use the array command on its own, then it'll start sending in a sort of random bytes will start coming out of the SPI port, and it could cause your device to hang, which is the problem I had with a flash chip. But the command byte array is the takeaway message. Use that one. So I am in my code. Let's just have a quick run through this, shall we? So the way I've set this code up is I initiate the chip first. So this is my chip select. So I'm going to take that low, and then I'm going to activate. Oh, the diction's off at the moment. Yeah, and this is just the intro screen of chip selects. That should be a 1 really for there, but it doesn't matter. Chip select should be off at that point. I'm just running through some LED just to make sure. As I've mentioned before, having a message come out over the UART or the USB port is a good way of knowing that your device is alive. So when you start doing debugging, then at least you know your debug port is fully operational. And I also make sure all my LEDs work as well. And so what I'm doing here is when I read my x-axis, I've got a bit of scaling, which I'll show you in a second. And then depending on what device you're using, to answer Greg's question earlier, on your data sheet, that there'll be what addresses, which are commands you need to send to your device. So you get that from your data sheet. So for my x-axis, these are in the data sheet, the commands I need to send to it. And then when I call my device, which is up here, so I send my to command config, because when you're doing stiction, it's pretty much forgetting everything. So when you come out of stiction, you've kind of got to reinitiate your device with any commands, which is what we've got here, to initiate all the commands again. And then I'm reading the ADC, depending on what address I've passed to the function, which in this case, reading the x-axis. So I've only got one bit of code. And then I'm having to read the address, read that data. I usually read it, here I'm reading it 100 times. So I'm doing a little bit of averaging. So I'm just reading the data in. This is all that bit shifting I was telling you about, shifting it 8 bits to the left, and then just adding the second byte, which we saw earlier. And then this is my 2's complement code. So all I'm doing, checking to make sure the number's is it a negative number? And then I've got my exclusive OR functions. And at the end of it, because I know it's going to be a negative number at the end, that's why I've got times by -1. And because it's a 12-bit coming out of this chip, the first 4 bits it doesn't use. So rather than having everything going up in sort of steps of 8, I just bit shift the whole thing right 4 bits. So I go up in counts of 1. So although it's 16 bits, it usually the first few bits they're not using. So you just need to do, again, a little bit of bit shifting. So I'm just reading it all, sticking it together, reading 100 times, and then taking an average, and then I output the result. So fingers crossed, this will work. So, right, just going to move that there. So this is it here. I'll hold it up to the camera, so hopefully you can see it. There we go today. So there's our device. So we've got our Pico here, and this is our other main board with our accelerometer on here. And if I press the button, it'll probably hopefully start streaming. So I've done a bit of scaling. So on this device here, I'll hold up the camera and you can see the numbers. If I tilt it one way, there you go, the x-axis goes up to about 90. So you can think of this as almost like a spirit level. There it's going positive. If I do it that way, it's going negative. That's the x-axis. If you look at the y-axis, it should start to go that way. That's plus 90, y-axis the other way. There, it starts going negative. And I've just scaled that just so it looks like 90 degrees. So it just easier to follow. And then this one's got a z-axis. So if I turn it upside down, then it reads minus z -1. We'll talk about RMS after our 2-minute break. So it's a very complicated way of making a spirit level. Right, okay. We'll talk about RMS after our break. Any questions there? No, nice and quiet. Good. Right, let me just unshare that one. And fingers crossed if I can reshare. Crikey. Right, this is when things are going to start sharing the wrong screen again, aren't I? No, so just share that one. Right, okay, so probably share the wrong screen. I've got a horrible feeling. Already got one on there. Right, what screen is that sharing? Oh, hang on a sec. Oops. Uh-oh. Right, so tell you what, I planned that would have a little break. And hopefully we can recharge. So, why isn't that working? Okay, that's brilliant. Right, okay, so tell you what, everybody, let's have a 2-minute break to try and recharge. So grab a glass of milk and a biscuit. I'm going to do exactly the same. And come back in 2 minutes and we'll have a look at part 2, where now we've got around the SPI, we'll have a look at an application for vibration. So I'm going to turn my headset off for 2 minutes and then grab a glass of water. We'll manage. Great. Okay. Oh, good timing, Stephen. Right. Okay. So this is a bit of a mess. This. I'm away. Right, 2 minutes is up. Are we all back at our screens? I hope so. So, right, okay, let me see if I can do the gymnastics again and make an absolute mess of this screen sharing. So, right, okay, so right, which screen am I sharing with you? The right one or the wrong one? Can anyone hear me?
The wrong one.
Splash screen.
The wrong one again.
The splash screen.
Oh, you've got the single screen on, have you?
No, you've got the dual screen with the presenter.
Not again. What is wrong with this? It's painful, isn't it? Right, let's try. Right, okay. Right, I guarantee that will be right, won't it?
Yep,
Right.
that's the one.
Yeah, that's the one. That's the one. Right, let's get back to welcome back from the break. Right, so time for a break. Break over. Back in the saddle, hard and fast. Right, remember this is what we started with different outputs. NO and NW were new out of the box and a little bit aware, and then the other one was when things are starting to go wrong. Now you'd think that if I just did some averaging on this for vibration using accelerometer rather than say as a tilt switch, depending on what your application is, if I did a bit of averaging, then surely I'll get a nice steady signal. So if we do some averaging, that will happen. Because you're getting a negative number out of these accelerometers, a positive and negative, of course, if you average, you're just going to get 0, which of course isn't terribly useful. So whatever you're doing with these things, you've got to come up with a slightly different way of trying to find what it's telling you. And somebody's done all that hard work for us. So it's a little bit of maths here. As I mentioned last time, when we're doing like AI machine learning, it's best to come at any of these problems, even vibration, from, I would say, as many different angles as you can, but without falling into the trap of representing the same data a different way. A little bit like, if you did a pie chart and a bar graph, it's exactly the same data, just presented slightly differently. So if you were to try and then draw some analysis, if you did that, let's say with a pie chart and a bar graph, you wouldn't actually learn anything new about your system. So it's a bit of an elephant trap. And if you dig around, sometimes you'll see, well, hang on, that's like variance, for example, is just the standard deviation before you apply a square root. So you wouldn't really bother doing variance and standard deviation. The reason why I'll probably use variance over standard deviation is because it's one less bit of work for the processor to do. So I haven't got to do the square root function. The most common one is the top left, which is the RMS. Of course, the mains voltage is an RMS voltage because the mains goes up and down. If you were to just do an average, then it would just be 0, and we all know 0 doesn't come out of the mains. So they do an RMS, which is, if it was a DC signal, what would it be? So the way RMS works is you square the numbers. So if you square any number, you'll always end up with a positive number. So minus 10 times minus 10 is plus 100, and plus 10 times plus 10 is 100. So it gets rid of that negative element, and then add all the samples together that you've taken. In our previous example, just before our break, we were reading 100 samples. We'll go back to that in a moment just so you can see it. And then it's dividing big N there to the number of samples. So we had 100, and then just take the square root. So that one I use all the time. The other one I look at often is what's called the crest factors, where you're looking at what the peak is, peak value. So if we went back to, just a second, I'll go back to that inner race problem. We might look at the peak and the RMS. So let's just see if we can go back and have a look at that. There we go. So that top right one, if you could measure the peak, well, the peak's clearly about 200 millivolts. but the RMS is probably around, I know, let's say 50, for example. So that crest factor would be 4, 200 divided by 50. Whereas on our brand new one, well, we've got all those crests about, say, 40, peaks 40. And that would probably, if you did an RMS on a new one, I don't know, I guess it'd be at least 20. So the crest factor would be, what, 20? 2 rather, isn't it? So 2 rather than 4. So coming at the data from lots of different perspectives and then doing some analysis, say with a bit of fuzzy logic, was how I would then go about sort of trying to determine, have I got a vibration issue? What is the characteristics of the vibration? As you can see, trying to work out the outer race, bottom left, difference to well, the bottom left of an outer race looks like, to me, like that characteristic is somewhere between a new system and one with a little bit of wear. So I'm not entirely sure how you could actually pick that one out. I'm sure there's a way to do it. So there we go. There's a for them in. I mean, my handy book here, which I've been doing wind turbines on condition monitoring. Actually, there's pages and pages of different equations, and as I was mentioning just a few moments ago, some of those seem to be slightly repetitive and almost telling you the same thing, like standard deviation and variance. Well, why would I want both? So depending on what you're measuring will probably dictate which one of these you're going to use. And if you're doing machine learning, I would probably do a whole load of them for the learning phase and then start to see which parameters are giving me the most information and like the maximum deviation, depending on what's happening with whatever, say, vibrating, whether it be like, you know, car engine or washing machine. And then if you go back to what we were looking at last time, if you didn't join us last time, you can go and look online and look at the stuff we did last month, where we looked at linear regression. So in this example here, we'll take the RMS calculation from before. Just go back to remind ourselves, top left. If we took that equation and plumbed it into our array, and then that array, then we would plot, we could then apply a little bit of machine learning to work out, is that vibration increasing or not? Is there a rule? Oh, yes. Okay, Richard, I'll answer that in just a second, actually. Okay, give me a second, Richard, and I will come back to that question. There are obviously non-linear curves as well. So if the computer responded, there we go. Data fitting. Right, so if you're learning something, the easiest is what's called linear regression, which is just a straight line equation, which is fairly straightforward to, there's a formula on the screen there for you. I have no idea how they came up with that, but trust me, it does work. And that was in my book on, which I've got with me, on teach yourself statistics on the section on linear regression. But of course, you might have a non-linear regression. So with some stuff I'm doing with wind turbines is things in the real world never degrade in a straight line. It's not a thing. So you probably want to try and know what is the best fit equation for my scenario. So I've been doing a little bit of work with that. You could, of course, if you wanted, with that non-linear one, try and fit a straight line to it. So that would be possibly a way short term, or maybe as a sanity check for, am I in the right region? But the worst thing you can do is on the right, which they call overfitting, which is when you've got all this data and you're trying to do a dot to dot and try and work out what an equation is dot for dot. So avoid number right on the right one, avoid that at all costs. To answer, where's that question gone? About the rule of thumb. Where is it? Hang on a second, it was here, wasn't it? Right, so Richard asked, is there a rule of thumb for the sampling frequency? Yes, so when you're sampling, there is something called a Nyquist rate, which means that your sampling rate really should be, or has to be, at least twice the frequency that you are trying to detect. So with a lot of these accelerometers, most of them top out at around, I think, about 5 to 10 kilohertz. So that's their maximum sampling. So you'd really wouldn't want to be changing your frequency much above maybe 2.5, maybe kilohertz to maybe 5 kilohertz. You can buy some high-end accelerometers, which I think go above 40 kilohertz and probably above that, but of course you're starting to pay for it. At the other end of the spectrum on sampling is most of these MEMS accelerometers will not work below around about sort of 6 hertz. They start to drop off in their sensitivity, because it's essentially it's a spring or a weight on a spring. And if you're moving really slowly, the chances are you're not going to detect much movement. But if you're moving quite quickly, then obviously the inertia of that weight on its spring will start to move quite a lot more. So trying to do really low frequencies is actually a problem for MEMS devices. Right, okay, tell you what we can do. Any questions there? And we'll look at some code for 10 minutes. Why not? Right, so let me stop sharing that. So say, just to go back before I stop unshare this. There we go. So the AI stuff, well, this stuff here, linear regression. So if you go back and download the episode 2 last month, it's got a lot more in there on regression. And there's also, if you have a look at the last month's MicroPython code, it's actually got it all coded up for doing linear regression. And also it shows you about product moments, which is how does one set of data compare to another set of data? So is there a trend, and can you spot it? So let me change that. Sharing screen share. Yeah. Right. Okay. So let us, for the next 10 minutes, look at this in a little bit of detail. Right, so going back to our program, I glossed over a few bits on RMS, root mean squared. So how am I doing that? Right, so here's the algorithm for it, and then we can see it all work and tear it apart. So I'm going to call, when I want the RMS, when I've calculated my X, my Y, and my Z to read them. As I mentioned earlier, for vibration, I've generally found you only need to use one axis. So in the example we've got here, I'm just doing the x-axis. You could do all three, and if you plotted them, you'd see they'd all still move up and down just by slightly different amounts. So you could average them all out to take the mean off them. And stuff which I've done, I've just found I'm just creating unnecessary work. So I just use one axis. And of course, a one-axis accelerometer will certainly be a lot cheaper. So where is it here? Right, so for the RMS, so all I'm doing is, and we'll have a look at this, I just call a function I've written called RMS. In my code here, if I'm doing something other than a variable, I usually put an extension on the end of it. So I know it's really for my own benefit. So I know I'm calling a function, although the brackets should really give the game away. But I also, if I'm doing IO pins, then I usually do my code. You'll see there's an IO extension underscore on the end. It just enables me when I'm coding just to keep a track of what's on IO, what's a function, what's a variable. It's not essential, it's just personal preference. Right, where is this code here? Right, so there we go, got time to look at this in a bit of detail, slow down a bit. Right, so what I'm doing here is, I'm actually going to do this twice, and I'll show you why when I'm doing the RMS, I'm doing it twice. So I'm going to read it once, and I'm going to, I've created up here an array, okay, called data RMS, and I'm going to have 2 elements in it. So I'm going to read the RMS twice, and I'll show you why I do that. So in my first round, if you like, I'm going to read the RMS 20 times. And I'm only reading the one axis, and that's the address for reading the x-axis. So I'm reading the x-axis, which means I'm then going to go and call the function. I think it's above this, isn't it? So I'm then going to call this function, which is going to read the x-axis. And don't forget, whenever I do this, I'm always exercising the stiction control, so it doesn't lock up on me. I mean, it might never lock, but if it does, it's annoying. And as we were saying earlier, after my stiction control, because I've basically cycled the power, it's probably forgotten any configuration. I just have to reconfigure it every time. So, you know, there is a downside, but at least then you'll know it's going to work. Here I'm reading it 100 times, and I'm doing a little bit of averaging. And then when I get to here, when I'm reading the RMS, I'm actually going to read it 20 times. So that there's a what, 2,000 reads here going on. I'm averaging, and then I'm doing 20 RMS averages. Yeah, you can follow that. So I do it once, and math.square is the function in MicroPython for the math library. And just to remind you, if you go to the top, that's how you just call it, import math. So only one sum, it's not maths, just the one calculation, clearly. We called it mathematics at school. Right, okay, so I read it once, and then I read it a second time. And the reason I'm reading it twice is because, as I discovered here, if it's stationary, then obviously I'll get the same number twice. And it could be about 0. If the thing was totally flat, I'll probably get the same number round about 0 twice. But if I was to angle it and say it said 90 degrees, say 90, if I did the RMS on 90, I would get probably, you know, so, and if it had like minus 90, because it's DC, I'd probably still read positive 90, whether it's positive 90 or minus 90. RMS, if it's stationary, will be 90, but it's not vibrating. It's not on the move. So what I discovered was, you can see here in the code, if I read it twice and they're both, and the difference between them is, say, less than 20, then the chances are that accelerometer hasn't moved. So then it doesn't matter what angle I'm at. So as you can see on the screen, I'm holding it still and it says 0. If I hold it here, see, it goes to 0. And if I give it a bit of a move, those 2 data points I'm reading, one after the other, are sufficiently not far apart that it knows it's on the move. But because one might be positive and one might be negative, and I don't know which way around it's going to be, I just take the square of it, and then I take the square root, which was saying earlier, if you did -2 times -2, it's +4, and then square root, I'll get 2. If I had a difference of +2, 2 times 2 is 4, and square root it's 2. So then I'm only dealing with a negative, with a positive number. Hopefully, something went ting in my ear. Hopefully that's just. Oh right, it lost the port. Hang on a sec. Something wiggled. Right, just restart it. There we go. It's back. So. To read the RMS, that's the only one I've done. What I have also done, I should say here, is, I probably don't need this now. I'll probably take this out and re-upload it to, what do we call it, Box online. I was originally just had it, if everything read, if it was just originally just sitting here with in the XY plane where everything read 0, that was originally just my reference. So this bit of code here, I should probably take that out now because I don't need that. That was originally there because I wanted to read the RMS value, but I wanted to use the RMS value as a reference, but I couldn't make it a reference until I'd read it. So I had to put a condition in, so it didn't keep crashing. But I've now taken that out because I was over at Hingston Hall this afternoon at a conference, and I just decided to rewrite the code during the conference, and now it works better. So I'll re-upload that. So that's how you read RMS. I haven't done the crest factor. To measure the crest factor, when we had the peak and the RMS, if you wanted to measure the peak, then I would probably think about reading the peak. If you read the peak value, and then when you read it again, is the peak value greater than the last time you read the peak? If it is greater, then that's your new peak. And so you can always find out what the maximum is, and you'd probably have a routine, I think, where you just update that every so often. Otherwise, you'd only ever have a peak detector. So maybe then every 30 seconds, you might just reset it and then find out what the new peak is. And then find out again what, maybe 30 seconds later, what's the new peak again. So with that, let's go back to it, shall we? Let's go back to here. So if I share that one. That's interesting. So I can't do that. Hang on, peeps. I'm trying to be clever here with the computer. Hang on. Well, no, I'm just trying to, but then I can't. This is rubbish, isn't it? Right, I don't know how that's going to work. So what I'm going to do, in the interest of time, I'm going to share this screen here. You can see this screen, can't you? So if we go back to this one here, if you want to do the crest factor of this one here, so you could every millisecond, 0.1 of a millisecond. So every so often with this IR one, hopefully you can see that one, you could every so often remeasure what the peak is by measuring the value before, find out what the peak is. We've just seen how to do the RMS, and then you could work out what the crest factor is. So again, with all this AI stuff, machine learning, machine intelligence, all it is just old school mathematics. So the stuff we played with last time, this time, and next time, it's just probability, which is what's coming next, statistics of what has happened before, algebra, and calculus. And for those who think what's calculus, calculus is about the rate of change of something. So, and there's just lots of formula to enable you to do that. Right, okay, I think that's what I've got for you this evening. Any questions? That's very quiet. You all still there?
Yes.
Anything you want me to run over again, or any thoughts, questions?
Hello.
Yep.
Thank you so much for this presentation. It's very clear. I just want to know if there is some libraries already ready for this example of accelerometer and stuff.
I'm sorry, I missed that. Say it again.
I want to know if there is some libraries already exist for in MicroPython or for this.
Right, are there any libraries? I don't know is the answer to your question, whether there are any off-the-shelf libraries. The way I've gone about it with, because I'm using microcontrollers, which are very limited on memory, all of my stuff that I work on is what I would call almost first principle. Because if I don't know if there's any libraries for a lot of these chips. If you picked up some of the stuff from Adafruit, for example, then I am pretty sure that their small modules will come with libraries. If you look around in like the chip which we've used here, the IIS, I think 328 it was, from ST Microelectronics, I'm not aware of any libraries for that one. But as we've seen in the code, and you can grab the code from the website, Silicon Cortex website, and downloads, it's not actually that difficult to write the code. You know, it really is just a few lines. And one of the things I would say, if you're using off-the-shelf libraries, is you'll probably find 90% of that library you don't want. So memory is very precious in these small microcontrollers. So do you really want to be filling it up with 95% of stuff you don't want?
Yeah, you're right.
Mm-hmm.
Yeah, you're right.
But it's quite educational as well to, you know, write it all yourself, because, you know, then you'll understand what's going on and be in absolute control of the device.
Yeah.
And of course, I'm willing to bet if you go on to, I don't know, so I might be doing them a disservice here. So I'll eat humble pie if I'm wrong. But I bet if you went onto Adafruit and you bought one of their chips, yes, you'd get the library, but I guarantee you'll have the stiction problem to deal with.
Mm-hmm.
So yeah, so, you know, getting free stuff off the internet's not always worth the saving.
Yeah.
Yeah, good question though.
Okay, thank you.
Yeah.
Hi, great presentation, thank you. The application I had in mind was measuring vibration of an internal combustion engine, a diesel engine actually. And one of the things I was worried about is temperature. How linear are these devices, and are they sensitive? Were there other problems that I might experience with the higher temperature?
Oh, you'd have to have a look at the data sheet for that. Let's see if I can find one here to answer your question. Yes. Right, so hang on a second. Just going to see if I can get the data sheet, and then I'll share the screen and we can have a look at that, see if we can find the answer together. Why is that screen blank? It's not been my day with a computer, has it? Right, let's see. That's a good question. Right, let me see if I can share share this. Oh, there's 3 questions here. Ditto thing. Okay, cat. Right, bear with. Let's see if I share. It looks like this screen here. All right, is that sharing a data sheet with you?
Yeah, it is. Yeah.
Yeah, good. Right, so look, it says here. Look at that. There we go. Extended range -40 degrees to 105 degrees. It says here.
Yeah, that should cover it then.
So yes, so well, of course, the thing to remember is, and this is obviously a word to the wise. Other components on your board might not be rated to a high temperature. So if you've got electrolytics, for example, on your board, depending on obviously the operating voltage and the temperature, those components will degrade.
Yeah.
So just be aware that there are other things on the board that will affect. I mean, obviously these sensors here, 3.3 volts. So it's not hard to find a capacitor which operates on at least twice the voltage. So let's grab a 10-volt one, easy. Then the temperature range of those other components, yeah, you need to pay attention to because they will degrade. There is also, we didn't talk about this, about the shock sensitivity of these devices. It's like 2G, 4G, and HG, this particular device that we've been playing with. And again, which one you use, it's selectable in a register. So over this PI, I can't remember what the address is. You'd send it an address, but I could probably find it here, just since we've got the data sheet open. I'll be here somewhere. Just trying to find the page that has all the addresses. And of course, when you want it, oh, here it is. Here we go. So these are all the addresses. So yeah, so this one here, I'm reading the X in 2 byte chunks, and then there are obviously configurable addresses depending on how you want to set up the chip. So I'd probably monitor the temperature in your application. That's what I'll do, Richard, for sure.
Yeah, thank you. Yeah, useful. Thank you very much.
And as I was mentioning earlier, the I2C addresses and the SPI addresses are different. So I learned this the hard way. So whilst they have, just find one here. If you're sending some of these commands, say we've got say 25 here, which would be 0010, wouldn't it? And then 0101. That's the address you would send if you send a reset. That's the address you would send over I2C. Over SPI, I've actually probably got to send it set bit 15 high as well. So I'd have to add 8 to that. So that then probably what that'd be A, wouldn't it? So it'll be A5 to reset it. So it's just another gotcha I discovered you've got to watch out for, because that might be different per device. Have you got one in mind you're using there, Richard?
I'm actually looking at an Arduino, the 33 IoT.
Right.
That would imply I would have to put all of the electronics onto the, because obviously it has an internal.
Yeah.
So on that would have, I don't really want to do. So that's why I was looking at something like this, that I could have a remote.
Yeah. So is that using the Uno device, is it?
Well, it's using the IO. Well, I have a couple on the. So actually on a boat, I have a couple already doing other things, and This, yeah, I was looking at using the built-in MEMS capability of the IoT 33 IoT.
Oh, okay.
But like I say, I didn't really want to put it on the engine because of temperature issues and that kind of thing.
Yeah, well, I'd monitor temperature as well. You could put temperature on. I mean, you could actually put both devices. Well, say put both devices on I2C. But the challenge, of course, is that I2C and SPI, they're not really, either of them are not really designed to be cable interfaces.
Right. Yeah.
If I was going to put one on a cable, I'll probably put the SPI on the cable because I2C is a floating, it's almost current drive rather than voltage level drive.
Right. Right. Okay.
So although it's more wires, I would probably put a temperature IC in it. Of course, most temperature ICs are I2C, not SPI.
Right. Okay.
Because they don't need the speed of SPI. So I looked at this and I thought, oh, look at that, yeah. So yeah, there's a few. Nothing's ever perfect, is it? There's always a compromise somewhere.
Yeah. 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 I'll keep. I think I need to hit the data sheets a bit more to
yeah. So if you're using the Uno, don't forget that's not got a lot of RAM. That's only got what 2K of RAM, has SRAM, and 32K of flash.
Yeah.
So for vibration, as I was saying earlier, you only really need. I've found, and I had this now to my washing machine, which is now broken. So I've got data for the washing machine slowly breaking. I found I actually needed one axis to get what I needed to know about the washing machine shaking.
Okay. Yeah. Yeah. I mean, I was thinking that I'd just offload the processing to another device somewhere, whether it be on the boat or remotely, and just the Uno or whatever would just deal with the raw data. So that was my question about what the sampling frequency would need to be, whether there'd be any scope for doing any processing.
Yeah, I have looked at sampling. Could I use like a Fourier transform to try and extract the frequency? The problem, with the approaches I've taken and outlined here and I've been using is because I'm doing a load of averaging, a load of data and averaging, trying to work out them frequencies thereafter. That's almost lost data.
Mm.
But I'm seeing enough vibration in the RMS to go, the time domain to go, well, that's clearly not good.
Yeah. So it's a general trend you're extracting rather than any detail.
Yeah, pretty much. That's how I've looked at it. So next time we're going out together, as it were, on our road show here, is we're actually going to look at sound. And so I have wondered about extracting frequencies. How can we do it with sound? So we'll have a little look at. I haven't designed a board for this yet, but I did it years ago on a BBC Micro. So I'm quite sure it's possible to do it on one of these little Pico things.
Okay.
Yeah, so we might be harping back to a little bit of the analog world and
Right.
analog filtering, for maybe some sound frequencies of sound. Of course, in your mobile phone, you can set that to a sound record and you can see frequencies, can't you?
Yeah. Yeah.
And in fact, I think if you use the accelerometer app on your mobile phone, you'll notice that the low frequencies drop off quite quickly, around about 6, suddenly they are so just drop off dramatically, don't they?
Yeah. Okay, well, thank you. Yeah.
No, that's okay. I'm here to help and answer any questions that come along. Right, what does Lawrence say? Lawrence said, scrolling through the messages here, MEMS microphones get blocked easily, so you might suffer from engine compartment gunge. That's one for you, apparently. Yeah, we didn't talk about MEMS microphones, did we, today? Right, I think that's great, everyone. Oh, right, okay. Anyway, right, it is 10:02. So quick question for those that left. So did a short 2-minute break do anything for you?
Yes, good idea.
Yeah, we'll keep that one, shall we? I was doing a bit of reading and I thought, okay, let's see if that helps recharge the batteries at all, because some of the stuff that we're doing, with talking about machine learning, we can't shy away from the maths. It's at the end of the day, it is all just old school mathematics. So yeah, so we're going to have to keep that little element, but so none of it's really rocket science. Doesn't need to be. Right, should we close there, peeps? Unless anyone's got anything else that they'd like to share. Nope. All hush. Good stuff. That means I've bamboozled you all. Right. Okay. 2 new messages. That's probably thinking goodbye. Oh yes, thank you. Where are we? Right. Okay, right. Let's all go put the kettle on, shall we? It's 10 to 9. 5. Yeah. Right. Brilliant. I will see you all next month. Let me just remind you what the date is, because I'm sure you've all signed up for it anyway. It is going to be the 7th of December. And I think we're going to be looking at what we could do with sound. So we'll do sound creation and we'll do sound detection. We'll see what we can come up with. Right. Okay. Cup of tea, everybody. Yep.
Thank you.
My pleasure.
Great. Good night.
See you next time.
Thank you.
Bye-bye.